Welcome to our electric car controller design presentation. We'll be presenting with Constantino, Karla, and Vianney. Our intro would be, thank you for picking VKC as your electric car supplier. This company was started in fall 2022 at ASU in the System Dynamics and Control Lab. We developed a user-friendly electric car control system that can be operated by anyone, even with someone with zero experience. It took a few iterations to get this far in development of electric car controller design.
Hello, you guys. My name is Constantino. I'm a junior mechanical engineering, a wizard in procrastination, and the lead engineer.
I'm Karla Chow. I'm a junior studying aerospace engineering, and I am a product manager at VKC.
My name is Vianney Ruiz. I am a junior/senior in mechanical engineering and French at Arizona State University in Tempe. I am the product designer of VKC, and I want the semester to be over.
A few customer requirements to take into consideration was reaching desired speed without demanding too much power and battery voltage. The driver needs to feel a minimum initial jerk, taking into consideration external conditions such as wind, slope, and making sure that the vehicle still reaches the desired speed. Minimal fluctuations in reaching the desired speed. You should have overshoot/undershoot in speed to be less than 2%. Rise time is larger than 0.1 seconds. 2% settling time has to be less than 0.2 seconds. Voltage required by controller has to be below 24 volts. Here's our setup. We had an Arduino with a PC, a 24-volt power supply, an Arduino, and MATLAB. Here is our feedback control system diagram.
So for the approach, we felt that proportional integral design was appropriate to do for the electric car controller design because it provided more accurate outputs over the proportional derivative design. So, and proportional integral design allows to reduce the steady state error and the rise time. For our system requirements or control lies where error equal to 0, settling time less than or equal to 0.2, rise time of greater than 0.1, overshoot of less than 2%, and a speed of 12 radians per second. For our trade studies, we had proportional integration feedback and proportional derivative feedback. So for proportional integration feedback, we found that in reducing both the rise time and the steady state errors of the system are useful whenever you need to change the magnitude and lag of the phase together. For proportional derivative feedback, we found that a derivative controller is required to minimize the transient errors like overshoot and oscillations in the output of the plant.
For the design requirements, we first initially started off with a proportional feedback, but realized it doesn't work because it was too difficult to get working. With proportional feedback, we had to add multiple inputs and outputs, and at the point it got to just did not work. So we went with proportional integrated feedback, which allowed us to have one compensator C and with a integrated of -1 and real 0 is -3 with a constant of 40. And for the filter, we didn't need no integrating or damping requirements. So all we did is just add a real pole from 17.9 to -17.9. And because of us putting this into system 2 requirement, our transfer function that was output was 16.5 parenthesis 1 plus 0.063 s divided by s. Arduino code, as we got our value from developing the MATLAB code, we input our found value into the Arduino as a KP value of 1.039, our KI as 16.5, KD 0, our float tau 0.1, our float min 0.6, and as we can see in the area, we have a desired speed minus our speed, and we produce a very good result from our desired speed developing the Arduino code and the MATLAB code. So as we can see in the first graph, angular velocity was the theoretical angular velocity was the time experiment and theoretical results. We notice our theoretical and experimental aligned up significantly close to each other with a wave like future on at 12 radians per second. And I mean that's how we know we did it right, because if the experimental value was off, we're not even on the line of 12, we know it wouldn't work. Since it's on the line, it's fully functional and it works. So as we can see, these are the system 2 plots found from the inputs and outputs we put into the proportional integrated design. As we can see that in the amplitude versus seconds, it met the requirement at 12 radians per second at 0.02 seconds. And that's another validation of our proportional integrated feedback. As we can see in the locus plot, none of our values is in the unstable region, everything falls under the stable region. As we can see in the magnitude, it just goes down significantly, which is a good sign. It's supposed to produce a linear line. As in the phase region is a straight line, which is a good sign. If it was a lopsided sign, it would have been a great result. That means we have reproduce it, but since everything fits our customer requirements, we are able to say proportional integrated design was the best way to go. Thank you guys for your interest in VKC. I hope you guys could invest in this, as our team put in so much time and effort into the product. And again, thank you for your time and pleasure. Hope to see you guys in the future.